Okay, the Hangout on Air is live. So, hello everyone on the VJug. Happy September, and a big welcome to Jonas Bonér. Jonas, how are you doing?
I'm pretty good, thank you. How about you?
Oh, very well, thank you, and welcome to the Virtual Jug. This is your first session, and
Yep.
we're going to be talking a little bit about resilience in this session. Um, Oleg, welcome as well. How are you doing?
Hi, Simon. I'm doing pretty well.
And how's Rebel Labs coming along?
Oh, Rebel Labs is fabulous. We are working hard and trying to provide you with good, opinionated content. So looking forward to making a recap of this session. I wanted to hear this talk for a while now, and now this is a perfect opportunity.
Awesome. So yeah, a couple of interesting blogs on Rebel Labs just recently. One about some Android libraries, some of the best Android libraries you can use, and one also about some of the preferred tools, command line interface tools that Bram enjoys. They seem to do pretty good.
Yeah, people seem to like those.
Awesome. So, so just before we get started, and I pass over to Jonas, then I'm just going to quickly share my screen so that people can see how they can interact with this session. Okay, there we go. So you can see my screen now. And what we're going to be talking about today is Resiliences by Design by Jonas Bonér. And you can follow Jonas on Twitter at jbonér. Is that correct, Jonas?
Yeah, that's correct.
Cool. I typed it in just before we went live, so I didn't check actually. So yeah, follow Jonas on Twitter, and just a couple of things to mention that VJug is sponsored by Zero Turnaround, and we have a media partner of Rebel Labs. You can go and check out some of the tools that Zero Turnaround create. We have a couple of free trial downloads that you can get, 14-day trial downloads, both JRebel and XRebel, so they're developer tools, so do check them out. ZeroTurnaround.com for that. For this session, you can interact with ourselves and Jonas on IRC, and if you go to a Freenode channel #virtual jug, you'll be able to discuss the session, ask any questions. If you do have questions, we'll ask them at the end of the session straight to Jonas. Please do share the session and the group on all your medias of choice, so Twitter, Facebook, and all the same. Let's turn this into a huge group. We're just over 4,000 people at the moment. And if you have feedback about the session or about the virtual jug in general, you can send them directly to the virtual jug at virtual jug, or myself on Twitter at sjmaple. So without further ado, let's talk about some resilience, and I really do hope of all the virtual sessions that we have, this session manages to stay up and we don't have any problems with it. That would be the ultimate in irony. So, Jonas, over to you. Let's talk about resilience.
Thanks a lot. So I'm just going to share my screen here. Can you see this?
We can, yes.
Okay.
Perfect.
Okay, yeah. Cool. Thanks for the introduction. So let's just dive right into it. We have a lot of stuff to cover. Most of you probably recognize this picture. It's about it's from this movie Rocky, and it's about this underdog that he gets a shot at a title. I think it's called the Italian Stallion, and so one of the most sort of memorable quotes from this movie is on the slide here, and I'll quote. But it ain't how hard you get hit, it's about how hard you can get hit and keep moving forward. How much you can take and keep moving forward. That's how winning is done. And this is fault tolerance. I mean, you get hit, you hopefully survive, you limp along for a while, and hopefully, eventually, you will win, right? The problem is that even though, I mean, most hero movies sort of has this sort of character, this sort of plot or theme, it's actually not a sustainable strategy. What we need is resilience, and resilience is beyond fault tolerance. And resilience is what I'm going to focus on in this talk. What it is, why it's needed, how other industries are dealing with it, what we can learn from it, and so on. And there's also So what is resilience? And if we go to Merriam-Webster for sort of the canonical definition of it, it says that it's the ability of a substance or object to spring back into shape, the capacity to recover quickly from difficulties. And the importance here is that resilience is about restoring full functionality, not just to limp along and sort of survive, but actually be able to fully heal, fully recover from difficulties. And you might have heard about this term anti-fragility, and being anti-fragile is actually beyond resilience. Even it's actually where the resilient resists shock and stays the same, the anti-fragile gets better, and it's been sort of popularized by this book by Nassim Nicholas Taleb or Taleb. And this is also a very interesting topic, but that's sort of, we as the software industries are, I think, actually not even close to achieving this, even though this is sort of the ultimate goal. So I'm gonna focus here on what I think can take us to resilient systems. Okay, and sort of starting with you probably heard about the happy path, right? And the happy path is also defined by Wikipedia as in the context of software information modeling, a happy path is a default scenario featuring no exceptional or error conditions and comprises of the sequence of activities executed as if everything goes as expected. Well, trust me, it never will. There is really no happy path, not even in the best of worlds, I think. And it really doesn't matter how awesome your application is that you just built, how beautiful it is, how useful it is, how scalar or elastic or non-blocking or highly concurrent or modular or whatever buzzword you throw in, right? It doesn't matter at all unless it's up, unless it's available. So it all really comes back to resilience, I believe. And it's actually, unfortunately, one of the most underappreciated and underestimated traits of software systems. And that's why I think we really need to go back to the drawing board and see how we relearn how we do things and how we can build really resilient systems. So Sidney Dekker, in an excellent book, Drift into Failure, writes about resilient systems. And one great quote is, and I quote, "We can model and understand in isolation, but when released into competitive, nominally regulated societies, their connections proliferate, their interactions and interdependencies multiply, their complexities mushroom, and we are caught short." The problem is that modeling the world is very, very hard, right? And systems of today, right? Modeling the world and also software systems are incredibly complex. And I really think that in order to fully understand resilience and how to build reliable systems, resilient systems, we need to study resilience in complex systems. So starting then, and what is complex and how is it different from complicated? So this is a complicated system, and it's usually sort of comprises of many different small parts. All parts are usually different, and each part has a very precise and defined role in the machinery. And it's usually possible but sometimes very hard, but usually possible actually to fully grasp and to fully comprehend, to understand it throughout. A complex system, however, is made of usually many similar interacting parts with simple individual rules, and these rules leads to emergent properties, and it's actually the interactions that produces a globally coherent behavior. And it's really impossible to fully understand the complex system by definition. And sort of this is an example of Conway's Game of Life, and I'm sure you've also seen it, right? And it's a very like a set of very simple and basic rules that's very easy to understand in isolation, like this glider, for example, or pattern here. But when we start combining these, right, even though the rules are extremely simple, they started to connect into like a sort of a global behavior that is impossible to understand. And it's very important to understand that complicated is not equal to complex, not even close. And we really need to think about them as very different things. Donella Meadows writes about when she writes about points for human intervention in complex systems, and I quote, counterintuitive. That's Jay Forrester's word to describe complex systems. Leverage points are not intuitive, or if they are, then we as humans intuitively use them backwards, systematically worsening whatever problems we are trying to solve. When humans get involved, we usually just makes it worse because complex systems are so hard to grasp, and we intuitively use them wrong. So I really think that we need good models to understand failure and in complex systems, what happens and what we can do about it. And I learned this model that I'm just going to introduce you to from Richard Cook. It was a paper he wrote, and also a great talk he gave that you can find yourself on YouTube, called "Operating at the Edge of Failure." And in Richard Cook, he's an MD, a doctor that's been doing like research in the field of resilience in medical systems for 20 years or more. And his colleagues, Rasmussen, defined this model in '97 as a way of understanding failure and why it's happening, right? So we have three different boundaries in this model. First, we have the economic failure boundary. You must stay within this boundary. If you don't stay within this boundary, you go out of business, essentially. You run out of money. Then we have this unacceptable workload boundary. This is actually where if you cross this, you fall asleep. And we as humans, it's also like you always need to trying to do like as little as possible to get the maximum impact. So we usually strive to again moving away from this unacceptable workload boundary naturally. But still, I mean, we actually sometimes cross it. I mean, for example, that happens in battlefield situations, catastrophes, or sometimes even like startups. I mean, startups shipping 1.0, and people like sleep in the office and stuff like that. And then we have the accident boundary. If you cross this boundary, then you fail. For some definition of failure, I mean, it can be you can define it in many different ways. It can be like nobody dies, or there are no outages, or we don't lose any business, or anything like that. And then you have an operating point, and this operating point sort of is moving between these boundaries, and is constantly moving. And then, as I said, if you cross the accident boundary, then you get a failure. And then we have three different pressures. First, we have the pressure for economic efficiency, like pushing the operating point away from the economic failure boundary. You know, management is always scared that you will go out of business, right, and try to cut costs and stuff, to be more economically efficient. So there's pushing the operating point away from the economic failure boundary. Then we naturally, as humans, have a pressure for like gradient towards least effort. We don't want to do more work than absolutely necessary. And these two tends to like push the operating point away towards the accident boundary. And then we get a failure. Like if we actually do cross the accident boundary, then everyone panics. We're starting, apply some sort of counter gradient, moving it away from the accident boundary again. That can be like adding new policies, rules, perhaps new tools, perhaps doing a rewrite or stuff like that. But then we forget about it. I mean, time passes, and after a while we say, that outage was last year, and it's not that bad now, and it probably won't happen again, and so on. And then the economic failure boundary start pushing us towards the accident boundary again, and history repeats itself, essentially. So one question then is why don't we have failures all the time? Since you will sort of expect this drifting to happen all the time. It's usually because we intuitively add an error, what we call a marginal boundary. So we have an error margin. at a safe distance from the accident boundary. So you can look at it like this big stop sign that we should not go beyond this point. This is dangerous ground, essentially. And the error margin is usually defined by rules. It can be like speed limits on the road, or I mean, say we should not use more resources than X, or we should not allow more users than Y, and stuff like that. And when we start getting close to the marginal boundary, that's a signal that okay, we need to pay attention now. We need to start improving resilience and look out for things. So then the question is, if we have this margin, why do we still fail? Okay. So I'm waiting for the animations here. So yeah, because you know what we know a lot about the marginal boundary, because that feels real, that feels tangible. That is something that we have defined ourselves through some policies and rules. But we usually know very little about where the accident boundary is. That's very, very fuzzy. It's really not until we actually do cross it and we get a failure that we know, okay, crap, here was the accident boundary, and then we can make a note of that and go on, so to speak. And you know, this push towards economic efficiency then drives us to try to cross this marginal boundary, just a little bit more and just a little bit more, right? And the way it usually works is that we try to cross it, and then we take a step back, and then we try to cross it again, and then we take a step back, and then we try to cross it again, and then we've crossed it so many times that it actually feels natural. I mean, we've been over this boundary now 5 times now the past month, and nothing happened. How bad can it be? Okay, so what happens then is that we move the margin, okay, and we move it closer and closer to the accident boundary, and we get less and less margin for failure. And this is what is called normalization of deviance. Diane Vaughan wrote about that and coined that term when she wrote about the Challenger launch decision. You know, this rocket ship that blew up, was it in the 80s or something? It's also called flirting with the margin more informally. And I think that this is a great model to have sort of in the back of the head, like why the failure happens and the psychology behind it. I think it's really helped me to really understand failure in a more like in a better way. So I really think that we need, since we're always operating at the edge of failures, really, we instead of trying to prevent it and see really sort of stay as far away as possible. Instead, I think we should embrace it. We should instead design for failure from the start and find a good way of managing it, since it's inevitable. It will happen. So, as an exercise, I looked at I did some research and looked at how some other sciences and fields and industries are dealing with resilience. You know, our industry in software is actually very, very young, and I think we have a lot to learn from other industries that have been around the block for quite some time. Biology, for example, or social systems. So starting with social systems, a friend of mine is doing resilience in social ecological systems and stuff. He sent me this sort of a paper called Dealing in Insecurity, and it had a very interesting model to understand vital services and how they keep us safe. And it defines sort of first 6 ways to die. There are 6 ways that we can die as individuals, right? Either being too hot, or being too cold, or from hunger, or thirst, or illness, or injury. Okay, and then so these are the sort of the 5 or the 6 different sort of pie slices in this diagram. And then we have 3 sets of essential services that sort of protects us from dying. The first one is shelter. That protects us from being too hot or too cold. Then we have supply, protects us from hunger and thirst, and then we have safety, that protects us from illness and injury. And these different services are laid out in layers that protect us from dying, because we have 7 sort of layers of protection, 7 layers of infrastructure that sort of protect us as individuals from dying. So going from top down, first we have the world. I mean, or in the world we might have things like energy markets, fuel markets, food markets, and stuff like that. Country, there were things like the military, regional, yeah, something like the police, for example. City, we might have hospitals, water plants. The neighborhood, we have food shops around the corner. You can go out and buy pizza or stuff like that. In the home, we have heating, toilet, tap water, and then all the way down to the individual. So, and this is really how the world works, and we don't think much about it, but we really have these layers of protection. And I think this is a very interesting model that, in my view, ties very much back to how I think we should write software systems, and I'll get back to that later. And in general, so Rainer Biggs defines 7 principles for building resilience in social systems, and we look some more, at least at the sort of top 3-4 ones here. The first one is like that resilient social systems always maintain high diversity and redundancy. You know, systems with many different components are generally a lot more resilient than systems with few components. You might ask why. It's essentially because it leads to redundancy. It provides sort of an insurance policy. You know, that where you have certain components that can compensate for failure in other components. That can sort of pick up. You know the saying, don't put all the eggs in the same basket. That's essentially what this is all about. And then the second one is managed connectivity. They always have really high connectivity. And connectivity, you know, can be both a good and a bad thing. I mean, the good thing is that it makes it easy to recover quickly from disturbances, from failures. But on the other hand, I mean, great connectivity makes it easier to spread disturbances, and that problems and failures spread as well. The third one, manage slow variables and feedback, is also very important. You know, sort of feedback between variables can either sort of reinforce sort of something, you know, failures or good practices, or dampen like negative feedback. And I don't have time to go through all of these, right? But in general, I mean, these systems are usually very adaptive, and they foster like complex adaptive systems thinking. It's also important, and that ties into, you know, going beyond resilience, like anti-fragile systems. A system that actually learn from failure and can adapt. So that was like a peek into resilience in social systems. So now I'm just going to give you a few examples of some interesting things I found when studying resilience in biological systems. So I watched this talk. It was actually a TED talk by Nicholas Peroni on complexity theory. And in this talk, he talks about meerkats. And I personally just love meerkats. They are extremely interesting and cute and funny animals. And this story about meerkats like shows resilience in the animal kingdom in a very good way, I think. And you know, meerkats, they are, apart from being like funny and sort of cute, they are very social animals, and they have very rich, pretty complex social behaviors. One thing, for example, is that it's only the dominant couple that are allowed to have babies. All the other ones are supposed to be babysitters and servants looking after the kids. And in this experiment, GPS was added to the meerkats, and the meerkats were observed crossing the road, which they had to do to go from one feeding place to another. And it was always the dominant female that led the group to the road. But once she reached the road, she stopped, and she gave way to the subordinates, to all these sort of servants. And the reason was simply that she wanted to make sure that crossing the road was safe, so she let the others try first, and if they made it all right to the other side of the road, she could cross safely. And you know, the dominant female is very important to this group. If she dies, the whole group is at risk, and it's really evolution that has produced this behavior for like thousands of years as a way of improving resilience. And here again, I think this is a very interesting pattern that I think can learn us a lot how we should develop systems in software. So we'll get back to this later as well. In general, what can we learn from biological systems? Yeah, one article that I wrote sort of lists actually very similar set of features in biological systems that are resilient as we found in social systems. The first one being that they always feature diversity and redundancy. The second, yet again, they're always very interconnected in sort of network structure where information can flow freely between these. And they usually display wide distribution of structures across all scales, even to very fine-grained level. And fourth, they have the capacity to adapt, to self-adapt, to self-organize, and to self-heal. All, as I said, very similar to resilience in social systems. So I think there's a trend here, and there's a lot of things that we can look at and try to apply to software systems. And Nicholas Peroni sums up his TED talk with this quote that I think is great, and I quote: "Animals show extraordinary social complexity, and this allows them to adapt and respond to changes in their environment. In 3 words, in the animal kingdom, simplicity leads to complexity, which leads to resilience." So let's now dive into resilience in computer systems, in software systems. Unfortunately, we often react like this. First not at all, and then with complete panic. And Richard Cook said in his great paper that I really encourage you to read, there's a paper called How Complex Systems Fail, that complex systems run in degraded mode. Complex systems run as broken systems. And this is probably the most important quote in this whole talk. So the essence is really that in a non-trivial complex system, like most software systems actually, something is always failing somewhere. They always run in degraded mode. They're always, by definition, broken. Okay, so we really need to fully embrace failure, as I said. And this brings me to the most fundamental lesson in this talk, and it's also the title of the talk, that I really believe that resilience is by design. There's really nothing that you can bolt on afterwards. It needs to be part of the design from day one going forward. Really, it's something you really need to architect around as a fundamental sort of trait. Sorry. And this photo, by the way, is from a home in Gilchrist in Texas. It was designed to resist floodwaters, and it was one of the few that survived Hurricane Ike in 2008. As you can see, it's all due to being designed for resilience. So let us now look at some patterns and strategies for how to manage failure and really sort of address resilience at its core. Okay. So because I really believe that we need to manage failure. That is sort of one of the key things here. So failure is inevitable. Failure is actually something that is natural, can actually sometimes be even beneficial. Not something that we like and enjoy, but still natural. And the important thing is that there's nothing exceptional about failure. Even though failures in Java and Scala or C++ and so are called exceptions, it's a really bad word because there's nothing exceptional about them. Failure is just a natural state in the life cycle of the application. As we learned from Richard Cook, systems always run as broken systems. Always something failing sometime, right? And I really think that we should look at it like that. It's natural, just like start, stop, pause, resume, then you have failed. And if you model it as being a natural state in the application's life cycle, then if you end up in that state, well, no big deal. You know exactly how to get out there. You're fully prepared to deal with it. Okay? So we need to design for failure, and we need a way of managing it. So another important lesson that I learned from this paper by Richard Cook is, and I quote, "Post-accident attribution to a root cause is fundamentally wrong, because overt failure requires multiple faults. There is no isolated cause of an accident." What is saying that there is no root cause, and I really believe that. I mean, complex system usually fails because how they interconnect with other parts usually. Don't even spend time looking for it, right? It usually just takes time to try to dive down and find the root cause, and you will most likely just be wrong and sometimes what you find is even misleading because the failure is actually somewhere completely different. Instead, again, spend your time developing a strategy to manage failure. So now let's look at a few patterns. So one of the core philosophies, in my view, of resilience is that we need to fully embrace crash-only software. Crash-only software is actually the name of a great paper by Candea and Fox. You can see the title of the paper. Actually, all the papers are referred like at the bottom, and I also have a long list of reference at the end if you're interested to read them. So in this paper, they talk about crash-only software as sort of being able to first crash safely, that is equal to stop, and start is equal to recover fast. And it's a way to escape non-deterministic bugs caused by inconsistent state. And it can be viewed sort of as a sledgehammer, but it's a very useful one, I believe. And a great quote from this paper as well, talking more about protocols that I will touch a little bit later as well. But I just want to, since it's from this paper, I still want to quote it. They say that to make a system of interconnected components crash only, it must be designed so that components can tolerate the crashes and temporary unavailability of their peers. This means that we require 1, strong modularity with relatively impermeable component boundaries. 2, timeout-based communication and lease-based resource allocation. And 3, self-describing requests that carry time to live and information whether they are idempotent. I really believe this is the way we should design protocols. There's a lot of wisdom here. and these two authors, they took their idea further in another interesting paper called recursive restartability. And what they do then is applying this crash-only pattern recursively at any level of granularity. It has the subtitle of turning the crash-only sledgehammer into scalpel, and I think that's a very telling title of the paper. And what this gives us is a way to like gracefully tolerate restarts at multiple levels in the system. And I'll get back to these patterns and build upon them just in a second. And another great quote from this recursive restartability paper is, and I quote. I quote, software components should be designed such that they can deny service for any request and call. Then, if an underlying component can say no, apps must be designed to take no for an answer, and then decide how to proceed. Either give up, wait, reduce, retry, reduce fidelity, etc. Essentially, applications, they must be allowed to say no. Sorry, I can't help you anymore, right? At least not for the time being. This also means that callers of this service must be able to tolerate to take no for an answer and still know how to proceed. And this gives us very resilient systems, I believe. This fundamental way of designing protocols. And Sidney Dekker said also in the Drift of Failure book. There's a great book I really encourage you to read. He said that explosive growth of software has added greatly to systems' interactive complexity. With software, the possible states of a system can end up become mind-boggling. And really, I think it's true. In my experience, almost all failures relate to some sort of state. I mean, it can be inconsistent data, partial data, wrong data, lost data, duplication of data that you didn't expect, and so on. And I think it's good to try to classify what we mean by state and their different sort of kinds. So one way of doing it, that's the way I look at it, is that we have sort of three sort of categories. First, we have static data, and static data is data that you read from config files. It doesn't, for example, right? You can read it from a static storage. It does not change. It's always available, and so on. Then you have scratch data. Scratch data is data that you use. It's a sort of temporary data that you use in computations. That's sort of transient. If you lose it, no big deal. You can just redo the computation. The interesting thing is in dynamic data, and dynamic data can also be like categorized in two different categories. You have recomputable dynamic data. I mean, dynamic data can be recomputed from something, sort of variation of static data. You could argue, but the most important data, dynamic data, is data that is not recomputable. This data, this is the data that you simply cannot lose. This data could be like data that the user gives you through user input, for example. If you lose that, yeah, what do you do? I mean, it's hard to go and ask him to fill in the form or whatever again, right? This is the critical data that you simply cannot lose. So let's now take a look at traditional state management. What we sort of are used to, I mean, the way we've been dealing with this in most sort of enterprise systems, I think, and JE systems and so on. So the legend of this is sort of so that we have this white sort of circle is the client, and in the blue one is objects in the system, and this red sort of square is critical states that needs protection, and then the dotted line is the way to explain where the thread boundary is. Okay. So now, I mean, in most traditional systems, we have like a whole bunch of sort of connected objects, and the critical state is usually like scattered all across the application. And now, if a client makes a request, coming in here and makes a request, then sort of that leads to some sort of activity down into this object model. That usually means that sort of like synchronous calls are made throughout these object graph. Okay, so now if something fails, what's happening? I mean, you know, they are all, this whole request chain is now all running in a single thread, stack frame after stack frame after stack frame. What's happening is if something goes wrong here, the whole sort of object hierarchy all the way up, or call chain, or rather say request chain, all the way up to the client is lost, because the exception like sort of blows the whole stack all the way up right into the face of the client. The problem with this, right, and unfortunately this is the failure management that we have grown up with, really, that I've grown up with at least, is that it's really utterly broken, I believe, because it really gives you sort of a single thread of control, and if this thread of control blows up, you're screwed, right? And what we then need to do to get away with some sort of sanity in the system is that we need to add try-catch statements almost anywhere, right? Wherever there's a call made that can lead to some sort of exception, we need to be ready there to catch it. The problem is that it's usually not the guy calling the service that knows how to deal with the failure that has happened, kind of way down in the object graph. It might be some external or third-party service that is down. I mean, what should the client do about that? So just throwing that in the client's face, I think, is completely wrong. And you know, since failure can happen anywhere, as I said, we need to add this try-catch statements almost anywhere. So they both are like completely scattered. So failure management is nothing that you can say here it what it is and really go to one place to understand it. And secondly, it's completely tangled with the business logic. It's really hard to know. Often sort of error handling is more than half of the code, and I really find that unfortunate as well. And I really believe that this is the wrong way to model failure. It's definitely not the way that history have taught us, like through other industries, how they deal with failure. I think requirements for a sane failure model is that failures need to be, first they need to be contained, so they do not spread, leading to cascading failures, like we see way too often, unfortunately. Then failures need to be reified. They need to be like materialized into messages, and these messages, failure messages, need to be able to be sent somewhere, like signaled. We need to be able to tell other sort of pieces, like other contexts or other sort of parts of the application that something went wrong. And they also need to be observed. They need to be a natural way to observe failures that is being signaled. And fifth, they need to be managed. And the interesting thing is that if you do all of these things, then you get a model where you can actually signal failure to another sort of context, a healthy context outside the fail component that is in great shape to just observe the failure and act on it. okay, outside the scope and the context of the failed service. And I'm going to sort of I founded the Akka framework, or the Akka runtime, or platform, or toolkit. It has many names. A few years ago, and Akka sort of embraces a lot of the concepts here. So to make it a little bit more practical, I will use Akka as an example how some of these things can be done. But as you probably hopefully understood, all of these patterns are very general patterns that can be applied in any language and on any platform, or using almost any tool. It's like a way of thinking about failure and thinking about how you design software. It's about principles. That said, if you're not familiar with Akka Actors, I'm just going to explain what an actor is. So actors are like very lightweight or reactive resilient components, and they are extremely lightweight in the sense that you can easily create millions of them. They only consume memory when they are passive. They don't like sit on a thread. They're very different from threads. They run on threads, but there is a scheduler that sort of allocates them to run on a thread when it's time, right? But when they don't run on a thread, they are suspended and put on the shelf, so to speak. And you can easily, as I said, run millions of actors on commodity hardware. And they are resilient by design, because they are fully encapsulated and contained. A failure in an actor that cannot possibly leak, unless there's like an out of memory that takes down the whole JVM. But then usually actors are distributed, so you usually run more than one. So the failure patterns still can be sort of scale up to almost any granularity. And the interesting thing is that they communicate through asynchronous message passing. So looking at the code here, this is a very simple actor. You just extend the actor trait, or implement the actor trait here, and you define a message here. And messages is for the actor's sort of a public protocol, so to speak. It makes they're exposed to a set of messages that it can respond to, and whenever that message is sent to that actor, it triggers a behavior. So this actor now, if it receives the greeting sort of a method here, or message here, it sort of responds to that by now logging out like hello and who it was, right? And you create actors by creating an actor system, and out of this actor system you can create actors. By passing in props, like sort of the actor configuration, you give it a name. Names are important in actors, and that creates the actor. So you have sort of factor, and out there, if you pass sort of the props into the actor of, you do not get an instance to the actual actor. Instead, you get an instance to something called an actor ref. So the runtime instance of the actor is fully decoupled from the reference to it. And this is great for a lot of reasons. It means that the actor can be restarted without affecting the client that's sort of talking to it. It's sort of because it runs in another context. It also means that these actors are what we call location transparent. That means that the runtime can allocate this actor wherever. It can run in process, it can run out of process in another JVM, it can run in another data center or whatever, and it can even move without sort of affecting this actor ref greeter reference. These are stable, while the actor can be allocated wherever needed to optimize sort of the throughput and so on of the application. And as I said, all messages that are sent to this actor are sent in an asynchronous fashion. And this is extremely important because it is this asynchronous boundary that gives us sort of the contained world, so to speak. I'll get back more to that later. So as I said, I mean, the first thing is that we need to contain failures. And this is to avoid them to leak and to cause cascading failures. And the key here is what we call compartmentalization. and you know, what we apply here is what we call the bulkhead pattern. The bulkhead pattern is really nothing new. It's really how the ship industry have been managing fault tolerance and resilience for years. And the way it works is that it divides the ship into isolated compartments And if one of the compartments are ripped up open and filled with water, the ship is still fine, because all of the other sort of contained parts are healthy, and if enough are healthy, the ship can just continue to sail along, right? And I think this way of achieving fault tolerance is good, but yet again, I think we can do better. I think we can actually have a way to not just limp along, so to speak, but instead actually heal these compartments completely and be fully resilient. And what we do, the way to do that is to apply a pattern called supervision, because you know we needed a way for failure to be signaled, observed, and managed by another healthy component outside the context that failed. You know, and this is what supervision is all about. It's to have someone else being able to receive the signal that something went wrong, and being able to restore, resume, or restart this failed subordinate and restore full functionality, full service. So like sort of let it crash pattern together with supervision or really give us systems that can self-heal, that can fully repair themselves as they are running, which is extremely powerful. So let me now explain how this works through the analogy of a vending machine. Okay, so let's say we have this programmer. He's really eager for coffee. So he walks up to this coffee machine and he inserts 1 coin, for example, or 1 quarter, or whatever, 1 Swedish kroner, and let's say it takes like two quarters. So what the coffee machine will respond with is like a sign or like a notification, say add more coins. Okay, the programmer adds more coins and he gets his coffee, and everyone's happy. So because if the programmer just insert 1 coin, he has not lived up to his sort of part of the contract, right? And then it's fine that the coffee machine sort of tells him that and sort of displays sort of an error that I expect more from you. Add 1 more coin and you'll be fine. Okay. So now let's say that this program comes up the day after now and inserts now two quarters. He expects his coffee, but now he gets sort of an out of coffee beans error, like thrown right in his face. What should he do with that? I mean, where is the coffee? I mean, probably stored somewhere, right? At some storage or whatever. I mean, how should he open up the machine? He doesn't know how the machine works and things like that. This is absolutely useless. This is useless information to the programmer that just wants his coffee. Instead, I really believe that the way it should work is that you in this sort of fictitious world, you might have this coffee machine service guy that runs around different floors, sort of, and he is the guy that should be notified through a beeper or email or whatever that this coffee machine is now out of beans, and he then should run up to the machine, add more beans, and the programmer gets his coffee, and everyone's happy. Okay. I really believe that is the way it should work, because it's a service guy that has the knowledge about how the coffee machine works and can deal with it and in a very efficient way. The programmer should not have to worry. Okay, I really believe this is the way we should define resilient systems and service protocols in general. That the client is responsible for validation errors, right? When he's not living up to his part of the contract. So errors should be thrown in the client's face. But errors are very different from failures. I believe that application failures, should not be thrown into the client's face, because they're usually just useless to him. What should he do? Like retry again. He has no clue what's going on. Instead, those should be sent up to what we call the supervisor. That is usually the component that created the service and knows why he created it. He knows like how it's set up, which services it's using in the backend, for example, and has a lot higher chance to actually deal with the error and manage that component. And if things are done correctly with the right isolation, the client perhaps doesn't even need to know. He might just. So this request can, in the best of worlds, perhaps even be retried for him, and he will get his response. I really believe that this is the way we should fully embrace and design systems. And Sidney Dekker again said that accidents come from relationships, not broken parts. Okay, I think there's also something to really keep in mind. So instead of having a sort of critical statement scattered across the whole application in many different parts, where a lot of sort of communication boundaries can go wrong, I really believe that we should define what's called the error kernel, like a minimal error kernel, and we should embrace what I call then onion layered like state failure management. Okay, and this error kernel, as I will show you in an example just in a second, holds this like non-recomputable state, the state that we just simply cannot lose. and it's called sort of onion layer state management because the error kernel itself never ever performs a dangerous operation. It always delegates that. So we know, right, that when the error kernel is hit with a request, we can always assume full correctness. The error kernel never talks to external resources. It never accepts direct user inputs. It always delegates to someone. So you get to sort of these layers of protections, or so you can say, that protects the innermost of this of your application where the critical state belongs. There's also a lot of great papers written about this. This idea comes a lot from Erlang, and we have adopted it in Akka as sort of the core way of doing it. So trying to explain it through some more concrete examples here. Again, we have the same sort of legend here. We have the client is the white ball here, and the object is the blue one, and sort of the red square is like the critical state that needs protection, which you simply cannot use. So now, if we work with this onion layer state management, we put this critical state inside the error kernel, so to speak, and then we have layers sort of protection where we like spawn up new services, which we delegate, dangerous work to. So now, if a client comes in and he does a request to one of these like bottom ones or top ones, depending on how you look at it, how you turn this thing around. The important thing is that you can see that the thread boundary here is actually isolated to each component. So each one of these components live in its own isolated boundary. This means that there's no such thing like blowing the stack all the way up to the user that used the component. Instead, failure can be contained within this component. And now we need a way that if failure then happens, it actually gets signaled and it's sent upwards. It always goes up. So it's always a supervisor that gets notified if something goes wrong. And in most cases, he might have enough knowledge and power to actually deal with the error. But it might also be that he doesn't, and then he can sort of escalate it higher up the hierarchy. The hierarchy. And in the worst case, I mean, for example, if it's an out-of-memory error, I mean, none of the ones in this layered architecture can actually deal with that. It will hit the error kernel, and the whole system will fail. But ideally then, so we'll talk about just in a second, you will run this on more than one machine, and you can still continue. Okay. So now this supervisor, since he will get notified outside the fail context, he's healthy, and he can actually deal with the error by just restarting the component, and the client's happy again and can continue using the service. Okay, and if you now remember, for example, how we talked about Meerkats, you know how Meerkats from resilience in biological systems work. This is the exact same pattern. Here we delegate dangerous work to subordinates in the same way as a dominant female delegates to these like Meerkats or servants, babysitters, and so we can ensure that the important components are always healthy. And if you remember, you know, the sort of the simple critical infrastructure map from resilient in social systems, we have these sort of layers of protection that protects us as individuals in the innermost core. This also brings us back to this model, like where we have sort of layers of protection protecting us. So I think these are like two very important sort of patterns that have been proven and to work really well throughout hundreds or thousands of years that we can apply in software with great efficiency. And just to take an example, Supervision in Akka works exactly like this. In every actor, they always have a default supervisor strategy. Whenever an actor creates another actor, it always becomes the supervisor of that sort of child, of the subordinate. But it's usually a good way to actually override the supervisor strategy, because, as I said, failure has semantics. Failures are just regular messages, I believe, that should be typed and that should have semantic meaning. So you should pay a lot of care to how you design your failures. So when a child component fails, the supervisor in this example here knows exactly what to do. So in this example here, let's say that this was sort of a supervisor model, some sort of math service. And if we, for example, here now get an arithmetic exception, then we can expect probably that there was like wrong user input or something that made it fail. Then it just tells this child to resume. If it's a null pointer exception, it's probably like inconsistent state or something like that. And then it restarts, and hopefully, like using sort of this crash-only recursive restartability pattern to restart and into hopefully in good state and can take on the next service. And if there's anything else, then this supervisor, he doesn't know what it is. Then he escalates higher up the hierarchy. Hopefully, someone higher up knows what went wrong and can deal with it. And in Akka also, I have to say that we distinguish between, the parent-child relationship. That there's always the parent that's responsible for the life cycle. He created the actor, or the component, and he's also then required to manage the rest of the life cycle, meaning stopping him, restarting him, suspending him, resuming him, and so on. But there's often usefulness into being able to use this thread, this failure signaling sort of horizontally as well. It might be other actors that didn't create the child, or sort of this service, that's still interested in knowing how is he doing. And since failure is just a regular message, it's very easy to just send that to whoever is interested. So you can actually subscribe to failures in other components, and that is done through this context watch. You can just have a look and put like a death watch is what we call it. And whenever that the child or whatever service you're using actually fails, you will get a terminated message, and you know that something went wrong. Okay. So, and this is all nice, I think, but this is not sufficient, unfortunately, because if you remember the lessons from resilience in social systems and biological systems, we need to maintain diversity and redundancy, and we need to have an interconnected network structure, and the same applies to software systems, I believe. You can never ever run a resilient system on a single node. Servers crash. Resilient app needs redundant copies of critical data, and replication is necessary for both availability and to spread of load. And in Akka, it's actually quite easy. I don't know if you remember at the beginning, or in the first example, actors always have names, and these names you can refer to in the configuration file. So in the outside configuration file, you can define an actor to become like a router, for example. So it can like spin up. That means that if it gets hit, it actually doesn't do the work himself. If it gets hit with a request, instead he delegates to n number of, in this case, like between 12 and 15 different sort of worker actors, and using now a round-robin pool, for example, to delegate the work. And since actors are actually so dynamic, this can even be done at runtime. It doesn't have to be done at configuration time. But this is also probably not sufficient, because what you want to do is what you actually want to be able to spin up these these workers on different replicas, right, to get full redundancy if one server crashes. And this is done by just adding a different provider. By adding, instead of the regular actor provider, you can have a cluster ActorF provider, and then you have to add some stuff like a connection point to the cluster through the seed nodes. But this is essentially all that's needed to have this router now being able to deploy on all the servers that are out there in this cluster farm. And if one set of nodes goes down, these actors will be picked up and reallocated automatically somewhere else. And from the client perspective, this just all works seamlessly thanks to the location transparency that is talked about in the beginning. That the actor F is like fully decoupled from where the actor is actually running, and the runtime behavior can be optimized accordingly by the runtime. But you know, I mean, it's still not just a walk in the park, because I mean, you know, one of the like fallacies like of distributed computing by Peter Deutsch is like the network is reliable. No, it's really not, right? So because as soon as you run things on multiple machines, you have the network in between, and you have a distributed system, and as we know, I mean, that's open up a whole new sort of category of failures. We get partial failures. Messages that are used for communication can be delayed, lost, reordered, duplicated, and failure detection is really just a guessing game, because it's impossible to know if an actor or a server running is actually being down and will never ever come up again, or it's just being slow because it's overloaded, or if it's doing garbage collection, is temporarily unavailable, will be back again in 2 seconds, and so on. So I really believe that we need systems that are fully decoupled, and they need to be decoupled both in time, meaning that the sender and receiver are decoupled in time. So you get this asynchronous boundary, and this asynchronous boundary gives us concurrency, and this concurrency gives us loose coupling, and this share nothing design. Actually, you have failure can be contained and isolated to not lead to cascading failures. And it also need to be decoupled in space, I believe. This gives us distribution. I mean that we can actually run it not just like through interleaving in time, but actually run it to multiple cores or multiple nodes. And this also gives us location transparency that opens up for a lot of interesting things. And here, reactive principles, that we are defining a reactive manifesto, leads the way, I believe. And I really think that we need to base it now in this new world of distributed system. We really need to base it on our communication on resilient protocols. And resilient protocols, in my world, needs to depend on asynchronous communication and eventual consistency for loose coupling. And these protocols need to be tolerant to both message loss, because messages will get lost, message reordering, because you can almost never trust that, and message duplication. And there's a new sort of term that has been sort of coming up in the industry called ACID 2.0. I don't know if you've heard that. Most people have heard about ACID, atomic, consistent, isolated, durable. But ACID 2.0 sort of means that A stands for associative, meaning that's sort of the communication is batch insensitive. You can actually batch operations without affecting behavior. C stands for commutative, meaning that it's order insensitive, and I stands for idempotent, meaning that it's duplication insensitive. And this really gives a sort of a lot of power to really architect fully resilient protocols, I believe. And one great tool in the toolbox here that fully embraces eventual consistency and asynchronous communication, as well as the sort of idempotency, is Akka distributed data. This is a new module that came out in Akka 2.4, and it gives you something called CRDTs. They stand for conflict-free replicated data types. You know that we've had as developers access to like key value stores that are eventually consistent for quite some time. DynamoDB and Riak and Voldemort and so on. And they are great, right? But they only give you one single abstraction that is key to value. CRDTs actually takes the same idea, gives you the same properties, safety properties, but gives you rich data structures. So you can have maps, sets, graphs, even and things like that, and they do compose. It gives you a lot of power to create rich data structures that has a lot of sort of correctness properties when it comes to distributed systems. So this is just a little example. It's actually taken from a blog that was just on Typesafe website, written by Patrick Nordwell, the guy that wrote the Akka distributed data. Instead of going through it, read the blog, and it's a really great tool to have in the toolbox. So I'm a little bit over time. Just want to before I quit here, I just want to say a few words on testing, because I think testing is extremely important. So the question is here, what can we learn from Arnold here? I mean, I think we should learn that we should learn to blow things up, to make things crash, right? And we shouldn't be afraid to bring out the big machine gun and try to shoot our app down, because if we do that, then we get a lot better understanding, when it breaks, where it breaks, and how it breaks. Right? Nothing beats practice, and actually going out there and start making a mess, essentially. And we should just learn to just pull the plug and see what happens. Like, perhaps not literally like cut the Ethernet cables, but you know what I mean. And this will usually tell us a lot. We should take notes, and what's happening is usually not what you expected to happen. Since in complex systems and with a lot of relationships, failures spread and usually materialize in the most surprising places and ways, I believe. And a lot of tools here can help you along the way. You have the Netflix Simin Army with the Case Monkey and the Case Gorilla and these type of things. It works great if you run on EC2. You have this load testing tool called Gatling, and also Akka provides, the Akka multi-JVM test provides some nice tools for simulating failures, simulating temporary network drops, and so on. And there are a lot of other tools as well. So you should learn to use them and use them. Essentially, pull the plug in random places and just observe what's happening. So we have covered a lot, but to sum things up, I just want to say that one of the most important things, as I said in the beginning, is to understand that complex systems always run in degraded mode. They always run as broken systems. And we need to fully learn to embrace failure. That resilience is by design. It's nothing that you can hand wave, nothing you can bolt on afterwards. It's nothing you can buy your way out of by buying expensive tools. You need to design for failure, and it's nothing more than a natural state in the application's lifecycle. Thank you. So yeah, I'll probably put these slides online. I have references for all my papers here. I learned a lot by reading through them, so I can really encourage you to dive into this topic in more depth. So I don't know if we have time for questions. Probably not.
Maybe a couple. We'll see. So thank you very much, Jonas. That was a great session. One of the questions, one of the first questions actually, is I think answered by that last slide you just showed, which is it possible to share the references to interesting books and papers. Presumably, we can either grab a list of them from you, or it'll be on SlideShare or something like that.
Yeah.
That we can grab. T-Grip on IRC is asking, with what paper or book do you recommend to start looking into?
Yeah, that's a great question. I tried to list a whole bunch of interesting starting points in this reference list, and yeah, I think it's best to just go through that. I've also given a talk earlier about distributed systems in general, and I think that there's a lot of interesting discussions from the references that I have at the end of that talk. You can find it on my SlideShare account. It's called The Road to Akka Cluster, and at the end of that, there's like 5-6 pages of some of my favorite books and papers talking about distributed systems, and a lot of them cover failures and building resilient systems. So.
Okay, and is that for Mohan's just added on IRC? He's looking for a book for programmers rather than research. Is there one you'd pick out for specifically developers?
Yeah, there are some interesting, more practical ones, right? I don't know if you. So, for example, this book is great. I don't know if you've seen that. Release It by Nygaard. That's a great book. You have Joe Armstrong's, Programming Erlang is also talks about a lot of the patterns we talked about here, and there's also some great books on Akka. Essentially, that gives you a lot of hands-on experience, practical experience taught through a sort of a great sort of more practical format, I think, with code samples and exercises and so on.
Okay, cool. A couple of questions from you, Oleg.
Yeah. First of all, thanks for the great session. It was really entertaining. So one of the questions is, maybe this is just an implementation detail, but like whenever I see somebody talking about Akka or actors, they usually show an example of the untyped actor, which receives the message, does something, doesn't majorly communicate back. So at the same time, I did a little bit of like not extensive research, and like one of the problems with that is that you won't get like great composability of that, because basically you're dealing, since you don't get anything back, you basically are dealing with side effects. So it's kind of hard to build a larger system out of that. So my question is it just for the brevity reasons, or do you think, like, and you actually think that we should all use type factors and go like one level?
That's a great question. You know, the canonical actor model is extreme actor model as defined by Carl Hewitt, and also that's sort of the way it's implemented in Erlang. That's been a great inspiration to Akka. Is extremely dynamic, and you can like spin up actors. Actors can redefine their behavior at runtime. They take another shape or form, and they can even like change the protocols. I mean, now this is a very powerful way to like implement state machines, for example. Now I can implement, and I can receive these type of messages in this stage, and then I move to the next one. I can apply. They can only respond to this other type of messages, like from like start, and then I can perhaps receive like resume and stop, right? And when I'm suspended, I can receive. I can only sort of reply, sort of act on sort of resume, like and things like that. And I believe that model is extremely flexible. But as you said, it's also a lot of sort of some problems lurking behind the scenes here. If you start writing large systems, then you need to be very careful in how you design your protocols, because the compiler that doesn't give you help, and that can lead to runtime errors. And I believe that the actors are the way I'm starting to use them is that they are extremely good, like underlying protocol, like a fabric. But there are probably more interesting sort of and better ways of approaching them than just using the raw form, at least in all situations. Like for example, we added Akka streams now. That gives you a way of essentially defining graphs of actor communications that are all typed using actors under the hood. This is just like a thin layer on top of actors, so you can use all the greatness of actors underneath, like the location transparency, the scalability, and the resilience, while getting typed. Another interesting sort of project is the latest work by Roland Kuhn, the tech lead of Akka. It's called Akka Typed, that actually also layer sort of typed approach to actors on top of the underlying fabric, so to speak. So there's a lot of work going on here, and some you can already use. And I can only say that I agree with you, and I know people that have felt the pain by writing large actor systems and without where things can start, go haywire when you reach a certain complexity level. So yeah, so we are aware of the problem, and we're working on it. And I think using actors for the right tool, I think can give you the best bang for the buck, while higher level abstractions on top where it's appropriate.
Yeah. Okay, awesome. So I think that pretty much wraps up the Q&A for now. We're about a quarter of an hour over, so let's wrap up there. Massive thank you to Jonas, and thanks for a great session. I love the slides, and thanks everyone for listening in and watching. And next session is going to be on the 23rd, Oleg?
Yes, it will.
23rd, and it'll be yourself giving a session on concurrency. So do check that session out. We're gonna end this broadcast then, and we're gonna jump straight onto an interview with Jonas, and you'll be able to check that out on the Rebel Labs page with with write-up or Oleg's write-up of the session. So do check that out, and the replay for this session will be on virtualjug.com. So once again, thanks everyone for listening. Thanks Jonas for giving us a great session.
Thank you. Thanks for having me over.
Oh, it's our pleasure. And see you next time on the Virtual Jug. Thanks everyone.
Thanks. Bye-bye.